two. What's up? More volume? Two. Give you more signal if you need it. Two. 1, 2, 2. 1, 2, 2. 2. Right, G. G, can you just take the fader down a little bit, please? A couple of notches. 2. 2. 1, 2, 2. 1, 2. 2. 2. 1 second. 2. 1, 2, 2. Two. 1, 2. Now I'll speak how they will speak, with the microphone slightly away from them. Two. Yeah, you really have to shout to get it to peak. 2. No. That's great, thanks, Stu.
The rest of them are enough for that, then?
Yes, please, mate.
Including the light turn lights.
Bring them very, very slightly down, but not a lot. Yeah, that's about right. Happy?
Coming in the gang then, all done.
Cheers, kind of done.
Hello, everybody. Welcome to BMVC 2018. Some of you have met me probably last year in the banquet. How many of you met me before? None. Okay, so we have one. If you haven't met me before, my name is Hubert, and I'm an associate professor at Laptev University. I'm also the program chair of BMVC 2018. I represent the program team to welcome you coming to this conference. Here I'm going to give you some information about the conference, and then we'll have the tutorial starting. BMVC 2018 is the 29th conference in BMVC, so it has a long history, starting from the first one in Oxford 29 years ago, and is organized by the organization BMVA, British Machine Vision Association. So we have the honor to host this conference at Northumbria University, Newcastle upon Tyne. It's actually the first time we host this conference at the northeast of England. So you should have visited the conference website. So most of the information will be available at the conference website, bmvc.org. We have a new system for question and answer in this conference. So basically, we'll be using Twitters. The way you do it is that if you listen to a talk and if you have any questions, you can go to Twitter and you can use the hashtag #BMVC 2018, if I'm correct. So if I'm wrong, somebody point me out. So hashtag BMVC 2018, and then enter your questions accordingly. Then your questions will be shown in the Twitter site, and then the session chair will be able to read out your questions. Or if you prefer the traditional way of raising your arms and ask questions, we also can do that as well. So it's just for both people if you wish to raise your arm or if you wish to go online. So you have your choice. We also have a YouTube live stream. So if you go to the website page, you probably can see our YouTube live stream, which is on already. The conference material consists of, say, for example, the online conference proceeding. So basically, if you wish to download a paper, we don't provide USB stick anymore because people just lost them. So we put all the paper online. So, and there are two separate ways to download. You can download the PDF for a particular paper. At the same time, you can download all the papers as a batch, but be warned that this file is actually quite big. It's something like 3 to 4 gigabytes. So during the conference, I would appreciate you download the paper individually instead of downloading the whole proceeding. The program booklet is available online and as hard copy. So you should have a little booklet. It consists of all the information that you need to know throughout the conference. You should have also the conference T-shirt and the badge. And also, more importantly, the dinner and drink tickets. So if you are registering for full, then you will have one ticket for Monday, one ticket for Tuesday, and one banquet ticket for Wednesday. So make sure you have them. If you register for day, then you don't have the dinner, so those tickets will not be there. So there are some reminder, the more important stuff. So you have the conference badge, which is the one that you're wearing. So please make sure that you wear them throughout the whole conference, and especially to the lunch event, the tea event, and also the dinner event. So we need to see your badge in order for the staff member to serve you. If you have any questions, if you wish to ask for help, then people with the red lanyard, they are the organizers. So you can ask anyone wearing a red lanyard like me, and they will be able to help you. A lot of you are asking for Wi-Fi. This one is actually the Wi-Fi. So the SSID is Wi-Fi guest. You need to open a browser then, and then you need to follow the instruction to register yourself with a username like an email or something, and then you set your password, and then later on you can just use this username and password throughout the whole conference. And finally, there's a reminder on the staircase. You can see that this is, we actually booked the whole building for the conference. Today we will be mainly here, but tomorrow some events will be upstairs, some events will be downstairs. So you make sure, please, when you're at the staircase, you keep on moving, because if you are not moving, people will be pushing you, then this will be quite dangerous. All right, so a little bit about this university which hosts BMVC this year. This university is called Northumbria University. It's where I'm from. It's a very young, fast-growing, and energetic university in North-East England. It's located at the city center. If you manage to come here, you probably know that this is the city center. We are right at the city center of Newcastle upon Tyne. Newcastle upon Tyne is known as a student city because we have something like 50,000 undergraduates here, and this university has something like 30,000 students. So it's actually a lot of students around the city. It's relatively safe, except if you get drunk, but if you don't drink too much, you're pretty much okay. So the Department of Computer and Information Science is the department to mainly organize this conference. We have 70 staff members, a rather big department as a computer science department. More importantly, we have over 40% staff member recruit in the last 5 years. When I say we are rapidly growing, I actually mean this. So we are recruiting quite a lot in the past 5 years. In fact, we're still going to recruit 2 more permanent faculty members by the end of this year. So if you're interested in jobs, this is a good opportunity. So we have strength in visual computing, computational intelligence, and human-computer interactions. We have a new building just for our department. So this is the building 1 year ago, and this is half a year ago, and this is essentially the building now. So I'm amazed how fast a building can be built. So it's just right opposite to this side of the campus. So if you're free, feel free to take a look. And you can see that Newcastle is quite a beautiful city as well. So if you have time, make sure you visit some of the sightseeing things, such as the riverside areas. So you have a lot of good restaurants and pubs over there, and also some of the museums. They're very nice as well. So there are 3 main locations for the conference. What you are currently at is the Student Union building, which is this one, the A1 here. The Student Union building is mainly for all the conference talks and poster and everything, and tea breaks and so on. And 5 minutes walking, we will have this civic center, which is where we will host all the dinners. So different from other conference, in BMVC 2018, we will have 3 dinners instead of 2, and we will have all the dinners at civic center. And we also have today's and tomorrow lunch at civic center as well. And the Northumberland building is just next to here, is for the workshop. So you don't need to worry about the Northumberland building until the last day. So you will have this program either online or on your program booklets, but I wish to go through some of the important stuff for you. So we will have, well, right now we are here. We just finished registration and we are doing the briefing. And then we'll have 2 tutorials, and then we have a tea break. The tea break will be upstairs. So you can go upstairs, and then you will have your coffee and tea. And then we have another 2 tutorials today. Finally, I will tell you how to get to the reception area, and we will have the reception starting from 7 at the Civic Center. Tomorrow, we follow a similar routine, but we start quite early in the morning, 7:30, so make sure you don't drink too much tonight. And the actual talk starts from 8, and then we have paper presentations and also the keynote. And more importantly, we have the sports night. So the sports night people should prepare tomorrow. And we have the poster session for poster 1. And then we have another oral. And we have the simple dinner at the Civic Center for the 2nd day. So if you are hosting a poster, if you are posting a poster tomorrow, you can start posting a poster in the morning where there will be more free time. So instead of doing it right before the poster session, I'll encourage you to do it around here for tomorrow posters. And then at the end of the day, you make sure you tear down your posters, because the 2nd day poster session will be here, and they will just throw your poster into the bin. So here people post a poster, and then we have poster session and another keynote, another oral, and so on. The last day is a bit different. So you can see that these 2 days, you have the lunch at the Civic Center because you have more time. But for the last day, the lunch is actually hosted here, just upstairs, and it will be a simple lunch bed. This is because followed by the lunch is the third keynote, so we don't wish you to go too far away and miss the keynote. So we prepare some simple lunch bed for you, and such that you can arrive to the keynote on time. And then main conference will be closing, and then we will have the workshop at Northumberland Building. So some of the reminders again. The Student Union Building catering will be on third floor, so basically upstairs. The Civic Center catering will be for the lunch tomorrow and the day after tomorrow, as well as all the dinners, reception, simple dinner, and banquet. When you go into the reception, make sure you remember to bring this Monday drink coupons with you. You can use it to exchange a drink of your choice. It should be in your registration pad. It has a highlight on Monday. And then you can just order whatever drinks you want. On top of it, we have other drinks and canapes as well. For the simple dinner, you have another drink ticket for you to exchange a drink. And we have a hot pot buffet. So if you wish to order anything more than that, you can actually pay for yourself as well. So they accept cash or card. Finally, for the banquet, you remember to bring this banquet ticket. And you need to put it on the table next to your seat. So because we have different meals selected by different people, some people select vegetarian meal, so they need to put the vegetarian meal ticket on the table such that this staff member will know what to serve. And we will have free course with wine. Actually, I purchased a lot of wine, so make sure you finish off them. And we'll have the award presentation there as well. So make sure you attend the banquet because you might be one of the person who gets the best paper. So the tutorials for today, we have 4 tutorials. Today we have tutorial from Vittorio University of Edinburgh and Google Research, Ivan from INRIA Paris, Abevnet from CMU, and Zetlab from the University of Amsterdam. So these are our sponsors. Finally, I need to thank for our sponsor who provides us a lot of resources to host the conference, so you can see them here as well. The sponsor table, they are also upstairs, third floor, so when you're free, make sure you have a look. They have some very interesting demonstration, and there are lots of job opportunities over there as well, lots of sponsors that are interested in hiring people. So thank you for your attention, and I hope you enjoy the conference. I'll leave the stage to Tim, who will host the next sessions. Thank you very much.
Hello? Okay, great. So I'm Tim Hospedales, and I'm very pleased to introduce our first tutorial by Vittorio Ferrari. Vito is a professor at the University of Edinburgh and a research scientist at Google. He's a leading member of our community, having won an ERC award and the Best Paper Prize at ECCV, and is the program chair of this year ECCV 2018. And today Vito will tell us about reducing annotation effort through human-machine collaboration and knowledge transfer.
Well, thanks, Tim, for introducing me, and the organizers in general for inviting me to this opportunity to present our work. So, I will introduce in general some tasks, go through some of the related work, and then present some of my own work. So, the task of scene understanding in general. An image comes in, the computer looks at it, and it should, for the very least, recognize the scene as a whole. See here, it should say it's a tennis match. Every object in the image should be recognized as belonging to certain classes, like person, racket, and ball, and also localized with a bounding box, at the very least, or even better, with a continuous outline. There are also backgrounds and surfaces at which these objects lie, like the referees against the wall and Andy Murray's on the court. These also need to be recognized and localized. Computer vision people pay particular attention to people. We like people. So in addition to boxes and outlines, we want to estimate the pose of humans, like in this skeleton example. Combining pose estimation, localization, and object localization is possible then to recognize actions. Here, Andy Murray is hitting a forehand. In a summary, the computer is supposed to recognize all the items in the scene and provide a description to the human. So this is difficult to do, mainly because there is some background noise, isn't there? Okay, well, let's continue anyway, it's not a problem, you know. So, this is difficult because of variations. So let's consider recognizing this Harry Potter book. You have a frontal-parallel view of the book, very nice and simple. Now you want to recognize it into this image. So this becomes more difficult because the appearance of the book has changed substantially due to changes in illumination, orientation, viewpoint. And there are also pieces of the image that makes it even harder. There are pieces of the image that are not the book. We normally call those clutter. And when the clutter touches the actual object you want to recognize, we normally call it occlusion. So because of all these factors, it becomes difficult to recognize the book. But there are good news. In the domain of recognizing smooth, nearly planar objects that are heavily textured, we solved that. I mean, not me personally. The computer vision community solved that recently with a technique called local invariant features. And the core reason why this can be done these days is because there is a clear closed-form mathematical formulation that tells you how to map from a local region on the Harry Potter book to any possible appearance of that region in any possible image. And that enables to build algorithms around it. So now the next step is to go for intra-class variation. So now you want to recognize not just one specific book, but cars as a whole. So here, there is no closed-form mapping that tells you how a Formula 1 car transforms into a police car or into a smart car. There isn't. The notion of car is defined by human definition of what it means. And therefore, you cannot build simple algorithms. You need to learn the transformation model from examples. That is why we need machine learning in the field and where the whole motivation for a lot of recent works that come out. So here is the simplest setting for learning visual models, fully supervised learning. You need an annotation to the same degree as the output you want on the test images. So if you want to detect objects up to a bounding box, well, you need to annotate the images up to a bounding box at training time. If you want a so-called semantic segmentation or panoptic segmentation model, then you need somebody to draw the precise outlines of every object and background region in the image. So here the human needs to take a lot of effort to draw all these outlines. How long does it take? Well, it's very expensive to do all this annotation manually. According to the ImageNet organizer, the famous challenge, they took approximately 26 seconds to draw a box with crowdsourcing or Mechanical Turk. So recently we have a recent paper called Extreme Clipping where we managed to bring down this cost to about 7 to 10 seconds, but it still takes a lot of time if you want to do millions of them. What if you want outlines? Well, according to the COCO challenge organizers, that's about 80 seconds to draw one outline with crowdsourcing. Just to put a ballpark, if you want 1 million of these, that's approximately 12 man-years of continuous annotation. That's a lot. And if you want full panoptic, so like in the recent COCO stuff work we did, so if you want every object and background region with an outline, there we are in the hundreds of man-years. It takes about 20 minutes to draw one of these. So the researchers in computer vision, they decided, no, this is too much, I won't stand for this, we need to cut this. And perhaps the biggest wave of work is so-called weakly supervised learning, where this time you provide an annotation to a lower degree than the output you want on a test image. So perhaps you want an object detector, but you only train it with image-level labels. Or you want your fantastic panoptic segmentation model, but again, you only provide a list of the classes that appear in the image and not exactly where they are located. Now, a lot of weakly supervised learning algorithms, essentially all, along the way to train the beautiful model, they also reconstruct the missing annotation on their own training images. Normally, I call this auto-annotation, and it's a core element. So instead of thinking of the human doing the drawing, now you can think of the computer doing the drawing. So there is a lot of works in this space. I like to take the tutorial spirit and give you some slides to find some of those that I like the most. So the basic step, if you want bounding boxes, is to operate at image-level labels. We discussed that. But there are also works that start from a point click in the middle of the object and try to reconstruct the box automatically, or works that take a video, like this nice jumping cut. It's a bit easier to train on video because you get some motion segmentation cues for free that tell you a little bit where the object is. So one thing we're going to look at today is weakly supervised by using knowledge transfer from other classes. So maybe you want to learn about the zebra and you have only the label zebra in the zebra images, But you also have many other categories like cats, where you have a clean bounding box, and you can use that to transfer knowledge. If people want a complete outline, there has also been a lot of literature. Again, most works are on image level labels, but people again employed point clicking, scribbles. You can even use object bounding boxes as weak supervision for segments, or again, some transfer or video technique. So these were these works that I call weakly supervised. They start from a fixed input. So a human provides the image level labels or the center clicks, then goes have a coffee, and the computer solves everything else. Instead, there is another level that's interesting, is human-machine collaboration, where you start from sort of weak supervision, but then the computer, along the process, asks a human to provide information during training. Perhaps it asks a binary verification question, or perhaps it asks to draw on a few images only. So when the human intervenes during machine annotation process, a lot of interesting schemes can be made, and typically performance gets better. Here are some examples of this. The perhaps most classical example of this is active learning, where the computer periodically during training queries the human for full labeling of a small subset of all the samples, maybe a quarter or a third or less. But you can also do other kind of labeling where you don't ask a full label. One thing we're going to look at today is box verification series, where the computer proposes some bounding boxes of its own, and a human only says if they're right or wrong instead of drawing them. Another big family of work is interactive object segmentation, like GrabCut, where a computer proposes an initial outline of an object, and a human clicks on the points where it's incorrect, and the process iterates between the computer updating the segmentation and the human providing the corrections. Finally, I also recommend what I call the Perona-Belongi school of thought, where they were managing to get annotations for fine-grained classification, such as a specific bird species, without ever asking for the name of the species and without assuming the humans would know about them, because many humans don't know the exact name of this one bird. So instead, they were asking attribute questions. They were asking which color is the belly, how long is the beak, is it in water? And from these questions, you can also deduce the label. That's a particularly interesting collaboration scheme. So this brings me to this talk. I'm going to present 3 of our recent works, all of them from this year. The first one is in the space of knowledge transfer, and the other 2 are in this modern space of human-machine collaboration. So let's go with the first work. So the problem setting, recap for weakly supervised, you have a target training set of the class you want to learn, here the motorbike, with only image level labels. From this, you want to somehow train a detection model, which is able then to detect and recognize motorcycles in new test images, where you have no labels at all. So that's weakly supervised. Now we are going to extend this setting a little bit into a knowledge transfer setting by adding a source training set of other classes which have bounding box annotations. Then we are going to try to transfer some knowledge from here to the motorcycle to help weakly supervised learning. So why is this relevant? Well, because making image level labels is a lot cheaper than boxes, in the 10 times cheaper. And existing weakly supervised learning schemes, they're getting better, but they're still far from the performance of full supervision. And in the end, we have millions of bounding boxes in existing datasets, so why not use them? So here is a crash course in one way to do weakly supervised bounding box annotation and detector training. There are other ways to do it, but this is perhaps the biggest bulk of works, the main mode of the distribution. So this is called multiple instance learning. You are given positive images with a motorcycle and negative images without. Then you decompose the image into, the image plays the role of a bag, and you decompose it into a large set of windows, which are so-called instances. You can get these windows with an object proposal generator, like ObjectNet or selective search edge boxes or more recent ones. And typically, this gives you 1,000 or 2,000 window proposals, which in their ensemble are likely to cover all the objects in the image. It doesn't mean they all cover objects. It means every object has one window somewhere in the big soup. So now the goal of multiple instance learning is to find the true positive instances, so the green one here, basically localize the motorcycle, but at the same time also train a window classifier, which then becomes your object detector later on. So within MIL, there are many sophisticated ways of solving it. One way that works well and is simple is to start a process by initializing the positive images as initializing a box on the positive image as containing the motorcycle. The whole image becomes the box. This works in some images, not in others, but it's a start. Then you alternate between retraining a detector based on the current localization and then relocalizing objects based on the current detector. And During relocalization, you can do many complicated things, but one thing that works well and simple is to pick the one proposal with the highest appearance score according to the current motorcycle detector. If you iterate between these two stages, you do it engineeringly well, you get to a detector that's much better than the initialization. So there are many refinements to this basic scheme, and I recommend two that tend to work well in practice and have been proven over the years. One is adding an objectness scoring function, and one is multifolding, which is due to Cordelia-Schmidt's team. Let me open the localization box and tell you more about how we do that and how we can use objectness there. So this is a blown-up relocalization stage. So at this point, you have your detector from the previous iteration, and you want to update the location of the motorcycle in this one training image. So what you can do is to take the current motorcycle detector A, evaluating proposal B on the image I. You can just take just this one, we're going to call it the appearance model, and take the highest scored one, and that does something. You can improve on that by doing a linear combination between your appearance model and a class generic objectness function, which also evaluates that proposal. So objectness is basically a generic function that gives a number, a continuous number in 0, 1, and it's higher on windows that are more likely to cover an object of any class. It could be a motorcycle, a teapot, a starfish, and this is in contrast with background regions such as sky, grass, and water. And the reason why you can make such a function that generalizes across classes is that objects have specific features that are distinguishing them from backgrounds, like having a closed boundary, looking different than the immediate surroundings, having decomposition into parts and such features. So we actually started proposing an objectness function back in 2010. Now better functions have been proposed later on. And we started using it to steer the relocalization process of MIL. So imagine at the early stages of multiple instance learning, the appearance function A is not very good. It's not a very good motorbike detector. So it risks to misfire in many ways. But if you use the objectness function as well, this steers the process towards picking objects rather than backgrounds and increases the chance that you hit the motorcycle. So over iterations, you get a better and better motorcycle detector. And in practice, this makes a difference of about 5 to 10% in the quantitative evaluation of your results, like a lot of works after ours also have shown. The key point about my talk here is that this so far was a manually engineered measure. So some people sat there and decided which features count for objectness. And now we get to the new element of this work. Now we are going to go back to our source training set, which has manually rotated bounding boxes, which we didn't use so far. Let's see what we can do to help the target training. So we are going to organize the source classes into a semantic hierarchy. For instance, giraffe is an animal, is an entity. And then we're going to train a single multi-class SST object detector over the entire source hierarchy. And we are going to do so in a multi-label setting where a sample that appears at the leaf counts both for that class and for every class up the hierarchy. So a giraffe sample is also an animal sample and an entity sample. You can easily modify modern object detectors to do multi-label predictions this way by changing the loss function to a battery of individual per class sigmoids instead of a single softmax. So if you do this, you can then run this class generic detector that you train now with an output label for every one of the class in the hierarchy on a target training image. What this produces is a single class agnostic set of object proposals, and each of them has a score for every one of the source classes. And you can use these scores to play around with knowledge transfer at various levels of the hierarchy. More concretely, we go back to our multiple instance learning relocalization stage, and we generalize the objectness function here to a knowledge transfer function K. Now, this knowledge transfer function is the score of the class generic detector trained on the source classes. So if you take the top level score, the entity score, then what you have here is a learned objectness function instead of a manually designed one. And in practice, it's going to work a lot better. If you use an intermediate level, for instance, vehicle, from vehicle to motorcycle, you have a finer level of transfer. And then you can also go to the leftmost level and say, what is the nearest source class to the motorcycle? Maybe you find bicycle. And then, again, you can use the same one source knowledge model to play around with all these levels for free. And this last level, the class-specific level, is perhaps the most common investigated area in knowledge transfer. So now we get to some experiments about this part of the talk. We are going to look at the ImageNet Challenge Detection 2013 dataset. It has 200 classes. When you do experiments in knowledge transfer, you've got to be a bit careful how you set them up so that you don't have leaks and the experiment is statistically valid. You need 3 sets. You need a source training set, in which case the first 100 classes of IRSVC, and there you have bounding boxes. Then you need a target training set, in this case the second 100 classes, and there you only have image level labels. Then you run MIL here, helped by knowledge transfer from here. You get some boxes, then you train a detector, and you run it on a separate target test set, which has these 100 classes, but without any labels. You just run it, and then you see how good the detector is. Here are just some qualitative impressions. This is the best MIL baseline we managed to build using the Edgebox object proposals with their own objectness function and all the tricks of the trade. And this is the same baseline, but now using a knowledge transfer function from class generic. And typically what this does, it localizes better objects, especially when they are small. In terms of quantitative analysis, what you see here is the performance of various versions of MIL. On the vertical axis is core lock, which is the percentage of objects that are localized on the target training set correctly. And here is what happens if you use the system I proposed to you without using a knowledge transfer function in the score. And it does something around 40. The exact value doesn't matter. What is interesting is if you use a class generic knowledge transfer function, things jump up to 70, which is a really much bigger effect that we thought would happen. So you localize, a lot more objects correctly with this. Also, target and test sets, target and source sets are disjoint in terms of classes. So interestingly, the other forms of knowledge transfer, class-specific and midway, are just marginally worse. We expected perhaps the closest source to work better, but it turns out that, of course, the way we handle it, the class generic function has a lot more training samples, are the integrated of all the training samples of all the others. Compare this to what happens if you use manually engineered proposals with a manually engineered objectness function. Interestingly, the proposals themselves, when you use the learned ones, they don't get much better. So you always get something around 40. But when you use the manually engineered objectness function, you only get a boost of 10%. So the real thing that makes the results much better now is in the knowledge transfer function at the entity level, which is inside MIL, and not in the geometry of the proposals, which is a nice lesson. Now we can take the boxes that come out of all these bars, train a detector, and then apply to the target test set, and then compare the performance of that detector to what you would have got if you would have trained with full supervision. And then you can see how good your model is. So full supervision would mean you manually rotate the boxes on all of the target training images. That gives you some value, which we call 100%. Now, a traditional MIL pipeline with manually engineered proposals and objectness score gets about a bit more than half, 55%, which is in line with the literature. And instead, with this knowledge transfer, we get to 80% of that ratio, which is not solved, but it's a lot better, and it's at a point where I think people can start using weakly supervised trained detectors confidently without being afraid that they lose too much performance. Some people, when they see the results, they come to me and they say, no, Vito, you're cheating. This only works because your source classes are too similar to your target classes. And I thought so too. So we started digging into this. And here what you see, for every blue point, you see a target class. And we look at the semantic similarity to its nearest source class. And that we write out. Then in vertical axis, you can see the improvement brought by doing the learned objectness function on that class. And minimum is 0, maximum is a lot. The point here is that there is no clear correlation here. It's not like a closed semantic class like Lesser Panda or Giant Panda benefits much more than car versus play track. So you do get a generic knowledge transfer effect, which excites me a lot because I thought this would exist since 8 years, but finally I found it. So it does work even across widely different classes. We also compare to state-of-the-art. This is perhaps not important to go into great detail. We looked at LSD and its variants, and also YOLO 9000, which also has a class transfer mechanism, and we perform much better than both. So one fun experiment you can do if you have a lot of GPUs is to say, well, let's not just do 100 sources and 100 targets. Let's go and try many more combinations. So we took 3 common data sets, and for each one in turn, we play the role of source or of target, and every entry in this table is a different knowledge transfer experiment. And here is the manually engineered ML baseline, and the net result is that the knowledge transfer helps all the time by a big amount. Surprisingly, even when the source is just 20 classes from Pascal, you still get an improvement when transferring to 80 from open images from Coco, or 200 on open images, or 600 actually on open images. So in conclusion, I presented to you a method that does knowledge transfer and substantially improves weakly supervised detection. You get detectors that are now usable, 80% of the MAP ratio compared to fully supervised. It generalizes across a lot of types of classes and even datasets, and you can use it easily. If you have an MIL baseline at home, you can quickly add plus K times to your relocalization stage, and boom, it works. So this closes the first part of the talk. Now I'll move on to the second part, where we're going to do some human-machine collaboration. So manual box drawing, as we said, we don't like that, very slow. A couple of years ago, we proposed box verification series. We start from a weak detector produced by MIL, and then we send the boxes that this detector produces on the training set, we send it to a human annotator for verification. The annotator says, okay, I think this box is correct, this box is wrong, and then you can use this verification information to improve the next iteration of training. So here, let's look a little bit in more detail what happens during relocalization. So if an annotator says, yes, this box is correct, then game over, you're done, you have your car, very well done. If the annotator says no, you gain some interesting information. We trained our annotators to say no when the box that displayed overlaps less than a certain threshold, let's say 0.5 IUU, overlaps less than a certain threshold with an imaginary perfect ground truth box. So if the annotator says no and you know the threshold, then you can do a little bit of triangle reasoning, and you know that every proposal that overlaps more than the threshold with this bad proposal, that proposal cannot be perfect box on the cut. It cannot be. So you can actually eliminate out, carve out a big chunk of your proposal set every time you get a no. So what does this in practice do? Because you iterate relocalization and verification, in the next iteration, the detector can no longer move just by a small amount. It has to jump to another mode in the four-dimensional distribution induced by the detector scores. And this enables you to jump around very fast in the space. In practice, you could also alternate retraining with this, but for this talk, to keep it simple, we just iterate between relocalization and verification. So here is how it looks in practice. The initial MIL detector says, is this a cat? The annotator only takes a couple of seconds because it's very fast to do verification, much faster than drawing, and boom, you have a box. In this case, the annotator says no, because this box doesn't cover a cat up to the desired quality. And then you go back to relocalization, you try the next mode of the distribution, and boom, you get the full cut. In this case, you get a yes, and so on. So on average, we have shown this process is a lot more efficient than drawing, but only on average. It's not faster on every single image. Let's look at what happens here. When you have a nice big object on an easy class like cat, here is the score of the box, this is the color, then chances are the first or second or third box will be correct, and then it's faster to verify. 3 times 2 seconds is better than 30 seconds. But what happens here? Here you have a difficult class, potted plant, on a cluttered images, and the score is not so good of your best detection, so you end up, it's not a potted plant, you end up saying no. Then the algorithm goes and proposes another box, and you go no. And then no, 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 no. This can take a while. And in fact, in the end, it might take you so many verifications that's not worth doing. It would have been better to draw on this image. Moreover, apart from the image difficulty, it also depends on how good your detector is. If you have a strong initial detector, you will prefer to do more verification. If you have a weak one, perhaps it's better to draw. If you want very tight bounding boxes, then perhaps it's better to draw because verification will take more iterations to get there. If you are happy with loose boxes, maybe it's better to verify. There are many different factors that contribute to the decision of what's optimal. This brings me to the contribution of this part of the talk, which we call intelligent annotation dialogue. You feed it an image in your current detector. This gives you box proposals sorted by the score here. And then we train an intelligent agent to find the best sequence of annotation actions to produce a bounding box in the smallest amount of time. So the actions the agent can do are verification or drawing, and it starts from the highest score proposal and goes down the list until the least scored. So here is an example of such a dialogue. You would take the IS call proposal and say, okay, send it for verification. Is this a boat? And the annotator says no. Then it gets to the second prox proposal. In this case, probably the human would say yes. If you say yes at any point, the episode ends and you have a box. If you say no, the agent can choose to ask your verification for the next box, or it could choose to give up and just ask for drawing. Just say, look, forget it, it's not working, just draw. And at any point in the series, the agent can choose to draw. And this is basically its main task of the agent, to choose at which point to give up. So we made two agents to solve this problem. The first one is based on explicitly modeling the duration of an episode in expectation. So let's assume you know the time it takes to draw a box, the time it takes to verify a box, you know it, and you also have a magic function that predicts the probability that a box will be accepted. Well, then you can write down the expected annotation time for any possible dialogue before it even starts. So you can just write down every possible dialogue, take the one with the lowest expected annotation time, and do that. The small detail here is that I said we need a magic function that in fact can be built to a good degree. You can build a function that predicts how likely it is that a box overlaps with the imaginary ground truth about the threshold, so acceptance probability, based on features you can measure. For instance, you can look at the detector response distribution. What is the score of the top scored box, of the current box? What is the score of the second scored box? What is the entropy of it? You can look at a class name, because some classes are just easier. And you can look at a box size. Smaller objects are less likely. So then you can set aside a small amount of data where you have ground truth boxes to train this predictor. And then once you have this probability, it turns out you can find an optimal rule with a very simple inequality. If the probability of acceptance is greater than the time it takes to verify divided by the time it takes to draw, then you should verify. If it's smaller, you should stop and draw. This is a very intuitive rule, and I think everybody can see it's true on one iteration, but it turns out you can prove that this rule leads to optimal behavior in terms of expected annotation time over all possible futures for that image. So integrated overall possible future moves regardless of the answer. So the proof is not particularly complicated, it's not particularly difficult, but it takes a couple of columns to write out, so it's in our paper. So the second way to do the agent, alternative way, is to forget about modeling. So this is something, model. The previous work was like old school machine learning. We modeled expectation, write down probabilities, Now you could say, we do not tell the model that the probability of acceptance is a crucial causal factor. We don't say that. We just let the agent figure it out. So we can do it with reinforcement learning. In reinforcement learning, the environment here are the sorted boxes and the annotators. The agent, as actions, can do verify or draw. The agent moves through a series of states. The state of the agent is which box it is in the series. And as a reward, it gets the negative time it took to do the move. And the episode always goes to the end when you get a box. So if you do this, you can then train it with reinforcement learning. And what this basically does for you is that it figures out how to associate the measurable image features to, in expectation, the best possible action to do for annotation. So here are some examples of the behavior of these dialogues. In this image, we need to annotate chair. And the computer looks at it and says, forget verification, the chair is too small. Even without knowing where it is, it figures that out. And boom, he asks for drawing. Here, you should annotate a horse, and the computer figured out there is hope for verification, so he asks one verification. He gets a no because it's not accurate enough. And after that, he gives up and asks for drawing. In this case, he needs to box a motorcycle. He starts with verification. He gets a no. But in the second iteration, the agents notice, well, I believe the second box is going to work out. So he asks for another verification, and he gets it. Here you can get even 4 verifications in a row. Not a sofa, not a sofa, not a sofa. Now it's a sofa. You can also get 2 verifications and then giving up and get a train. So any kind of length of the string can be found by this strategy, and is found automatically by it. So here we get some quantitative experiments. We annotated approximately 5,000 images, 7,000 boxes on the Pascal 07 dataset. We take 10% of the data away for training the agent. So we train the probability of acceptance in one agent, and we train the reinforcement learning policy in the other agent. We wanted to show that this model is good for flexibility. So we try 2 to the power of 3, 8 different scenarios. One, we vary the desired quality. we set the threshold for accepting a box above IUU 05, which is okay, but not great, or above IUU 07, which is really tight. Then we tried with a detector which is trained from MIL, which is a weak detector, or you can take a strong detector trained on Pascal 2012, which has the same classes, but different images. You can also vary the drawing time. You can draw with the original interface used for ImageNet, approximately 26 seconds, or with the new interface I did not present today, which we made last year called Extreme Clicking, which can go down to as low as 7 seconds. For every combination of these, you get a different scenario. Can we train an agent to behave well in all the scenarios? That's the game. So here, the numbers you see, these are 6 of the scenarios drawn here. The number you see is the mean annotation time and standard deviation, because we did some resampling, but it's always pretty low. So we compare the agent to 2 standard strategies, always drawing or always doing box verification series until you run out of boxes, and then you just draw at the end if you're really bad luck. And what comes out here is that the agent, both of the agents we have, always outperform the standard strategies in all the scenarios. That's good. Not by a lot, but they always do significantly. So sometimes people tell me, this is too complicated, it works, but look at how much I need to work for this, it's too difficult, I'm never going to code this up. So some people say, why don't we have fixed strategies? I do 1 verification, and if that fails, then I draw. Or I do 2 verifications, and if they both fail, then I draw, or 3. So you can do fixed strategies that have the spirit of our work, but they do not look at that one image. And it turns out that they work well. But every time a different of these fixed strategies is optimal for a different scenario. So you still need to figure out which ones to use. Whereas the agent is almost always the best or equally best because it continuously adapts to the scenario at hand. In fact, it's best in 5 out of 6 cases. And that is this flexibility we wanted to get. In case you wonder, the 2 agents are statistically indistinguishable. They are equally good. This made my student very sad because she thought that reinforcement learning should always win. Whereas I thought, I'm very happy. Look at this baby. He didn't know that probability of acceptance is important. And yet, it matches an agent where we bake that into the model. It's beautiful. Reinforcement learning is great. So another thing you can ask is, what's the lower bound? I know what is the optimal strategy if I have the ground truth, and I do. I just was hiding it, right? So it turns out that our agents are very close to the lower bound. Often, they are statistically indistinguishable. So now you will say, Vito, we don't have a fixed detector. We don't have MIL or Pascal 12. Real life is more complicated. The detector gets better over time. And indeed, that's what happens in real life. You train a detector with a little data, what you have. Then you apply to the next batch, and then you have more data, and then you again update your detector. So that's exactly what we did, doubling the data all the time in 6 iterations. And ideally, we want to see that the agent can adapt what it does to the change in distribution of the detector response. So if you look at this in a summary view, on the horizontal axis, the annotation time on Pascal 07, vertical axis, how many boxes you made. You can compare to slow drawing, pure box verification series, or this fast drawing method, extreme clicking. And the agent outperforms all of them in terms of performance. It's a little less than double as fast drawing. So by now, we can make a box in about 4 seconds, something there, like that. And I think I'm done. I think I will not write papers on bounding boxes anymore. If I do, you feel free to email me to complain. And you may wonder, are these boxes any good? Well, they are above IUU 07. That's by construction, good. But can you train good detectors out of them? So we took the boxes that came out of this pink line, trained the detector, and then applied to the test set. And this gives you a detector which performs on 98% of the MAP of always drawing, of a detector trained on always drawn data. So it's basically at the same level. So one thing that made me really happy is to look at the adaptation effect. So in the first iteration, 3% of the data we always draw. And then we let the agent choose what he wants to do, right? In the next iteration, the next 3% of the data, the agent notices the detector is terrible. So X stands for drawing and V for verification. So here you can see the mixture of moves it makes. In the next iteration, it says, well, this detector isn't any good. I'm just going to draw mostly. But as the iterations pass, here is 6%, 12%, 25, 50, keeps increasing, then the detector gets better. The agent knows, automatically figures it out, and mixes in more and more and more verification moves by himself. And that's what brings you the speed up. So this was the second part. The third part is the shortest, so we're going to fit in. And it's also about human-machine collaboration. This time, it's for full image annotation. So not just one box. It's for about annotating the outline and the class label of every object and background region in your image. So this We actually did this in a paper called Cocoa Stuff this year, where we augmented the Cocoa dataset with background regions. And the total sum of foreground and background regions in total is about 19 minutes to be done by hand on crowdsourcing, so it's really expensive. How does a traditional annotation system look like? For instance, Label Me, where you draw polygons, which is what was used for Cocoa, basically. Well, here comes an image. You draw a polygon on the laptop. Well done. 80 seconds have passed, but well done. Then you keep clicking. You click for a while, and hundreds of clicks later, boom, you have this beautiful pointy cat annotated image, and can run a challenge and have fun. So here instead we propose an alternative to this tedious process. The image comes. We start from a pre-trained segmentation model, and train on external data. Then we run it on this image, and this gives you an initial segmentation, which then the annotator can edit with intuitive edit operations I'm going to show, and just a few tenths of mouse clicks later, you have this approximate segmentation. So the general design principle behind this, we call it fluid annotation, is to have a strong machine learning aid in the form of a pre-trained segmentation model that does the initialization and also assists the edit operations. Also, previous annotation schemes typically had a predetermined series of annotation actions, like indicating that the object is present in the image and then drawing a rectangle or a polygon. Whereas here we want to have, instead of a series of predefined actions, which are atomic, we thought we would just have a single interface that enables you to do full image annotation with a single pass. And then the last point, perhaps the most interesting in the design, is that previous annotation schemes, including active learning schemes, including the one I just shown you before with the box verification, they give the power to the computer. The computer decides the sequence of questions. The annotator is just a poor drone, sits there and must answer. So here instead, the annotator gets to see the current best segmentation by the model at a glance, and then it can decide what to annotate, what to correct, and in which order. So if you do this, what happens is that the annotator focuses on the regions of the image that are incorrectly annotated, and therefore provides information exactly where the machine doesn't already know. This makes it more efficient, and apparently the annotators are a little less unhappy of doing the job. So how does it work in more detail? We train Mascar CNN on a little part of the dataset, which we modify to output not only object segments, but also background segments. And on average, we get about 1,000 segments per image, along with a class label and the detection score, which we're going to use. Then we make an automatic initialization. We take these segments and paste on the image the top score segment, then the second top score segment, and so on, until we fill nearly the whole image. And every pixel is assigned to exactly only one segment. All the other segments, they are behind in depth. Imagine a depth ordering on the segments that goes behind my monitor here, and they are sorted by detection score. So now, this is the interface. The human has no button at all. The human can correct the current segmentation with 4 possible actions. He can hover the mouse on a region and reorder it. He can click on it and scroll his mouse wheels to put it at depth, at which right depth. So in this case, it pushes this person forward. Then he notices, wait, this is not a person, it's a blanket. So he can click on the label and change label. Now, it doesn't need to choose the correct label out of the 190 Cocoa Stuff labels. That's too much. Here, the computer assists again by showing a short list which is sorted by detection score according to the current model among all the regions that overlap heavily with this one. So now you only need to move your mouse a little bit, and after a couple of scroll wheels, you find the blanket and you have it. Another thing you can do is to remove action, like right mouse button, boom, this piece of a wall is gone. And perhaps most interesting, the add action. Here we miss a keyboard. The human knows it, clicks on it, and immediately gets the highest score region that's roughly centered at that point. You can play with schemes on how to combine the score of the detector and the centeredness. In this case, it says cell phone, nah, not quite. So you scroll your mouse wheel, you get a keyboard, yeah, but it's not such a pretty keyboard, so you scroll one more, and after 3 scrolls, you have your keyboard there, and you confirm. If you continue like this, you take about 15 interactions with this image to get to this final result, which looks quite good. Here is a video of a real human annotator in action. I'm going to slow it down. He's annotating a salad. Salads are really good because computer vision models are not so good at it. And so there are a lot of errors to be corrected. And you can see how much fun this annotator is having, hovering around, adding various items of foods. You can see how he scrolls the wheels and gets all these regions appearing. And after a while, a couple of minutes, it's done, and it gets a nice salad out of this. This was a qualitative example, but we also ran many quantitative experiments. Here is one big summary. On the horizontal axis, you have a unit of cost, which is the number of GUI events on average per image. Every mouse click, every scroll wheel, every character keystroke, everything. And on the vertical axis, you have a measure of quality, which is the recall of all the object regions with the annotation, which I won't go into the details. So the standard polygon drawing interface grows linearly, and it takes a lot of clicking, and fatigiously, finally, you get to the best result. If instead you use the fluid annotation interface, you start from a much higher point, then you get this nicely curved, slightly superlinear growth. At top point here, performance is a little below the full polygon drawing, but it's at a very good point. It's something like 95% of it. It's about 3 times less GUI actions. You can also run a simulator instead of a real human. You can run a simulator that knows the ground truth annotation of the image and picks always the best interface action to greedily move up the objective. And it's interesting to see that the human and the simulator behave very similarly. The simulator is obviously a little bit better, but the curvature and the heights are comparable, so it's nice that because it means you can design interfaces using simulators. You will say, we don't care about GUI events, we care about time, because time is money. So we also measure time. And here what you see is expert annotators we just used to do fluid annotation on Coco stuff, the same experts doing polygon annotation, and that 3 times factor that we observed is also observed in annotation time. Interestingly, if you look at the time reported by the Coco staff paper, which uses essentially this interface, but on crowdsourcing, that's another twice as low. This is very common if you do things in-house with your students, or if you do it, crowdsourcing is always about twice as low, but the ratios they preserve. So how good is the quality of the annotation? One thing you can do is measure the consistency, the agreement between experts along all pairs of this annotation triangle. So you have the original crowdsourced annotations of Coco stuff, the reproduced polygons by our experts and our experts on fluid, and on every edge you have the average number of pixels that have the same label, and you get about the same values, which means that none of the interfaces are particularly negative bias. They all have some disagreement point, but on average, they're all equally qualitative. So you will say, where is the disagreement? 70% agreement doesn't seem so high, but in fact, it's consistent also in several of the Torralba papers. You can find this number. Well, people agree on boundaries where they are, but they disagree on the exact name of the class if you have many classes. Here you can see the original image. Here, in the fluid annotation, the annotator said this was a playing field, which is good. Another human annotator, when using polygons, he said that was a grass field. You know, whatever. They're both fine, but these pixels would count as disagreement. Similar, on this complicated indoor scene, you can see that fluid annotation can give you at least an approximate outline of the nice Christmas decorations here and find small objects like books. And the disagreement indeed is about the exact meaning of classes. Like one annotator here thought this was a blanket, another annotator just said it was cloth. Well, you know, cloth. So this brings me to the end of the technical parts of this work. And now I would like to conclude with one slide advertising a data set we just made and we released recently. It's a hobby of mine. And it's called Open Images. We released version 4 about in May, and we are having a challenge at the CV now. So this data set has 600 object categories and about 15 million bounding boxes over about 2 million images. So most of these bounding boxes have been drawn by hand, which I know a little bit breaks the story of my own talk, but you know, whatever. About 10% have been made with box verification series and the rest with the extreme clicking. And this is about 10 times larger than existing data sets. And it has complex images. On average, we have 8 boxes in every image, so you can do contextual reasoning. Just recently, we added visual relationship detection annotations. So we don't only know there is a guitar and a man in this image. We know that this man is playing this one guitar. This other man is playing this other guitar. This chair is at this table. This chair is at this other table. So we have these associations between pairs of objects, which are also part of our challenge. So we hope you enjoyed this dataset. It's completely free. You can download it online at that address. This brings me to the end of my talk, and I will take questions.
All right, thanks for that great talk. Does anyone have some questions for Vito? Okay, I got one coming in by Twitter. I think this question is with respect to the first part of the talk about the knowledge transfer. Can you elaborate what you mean by semantic similarity between categories?
That's a very good question. It took us almost a full page in the paper to convince the reviewers. So, in that experiment where you saw semantic similarity, probably you mean the scatter plot we had. Anyway, there we used the link similarity, which is basically a distance along the WordNet tree, roughly weighted by the inverse number of samples in it. It's something that people in the computational linguistic literature use. So basically, bicycle is closer to what was I saying, motorcycle than to cat. So it's basically the distance along the tree. However, if I can hijack the question, we also tried a number of experiments with other definitions, including appearance similarity instead. We said transfer not from cat to dog, but from the globally most similar appearance. You cannot use the box, that would be cheating. But you can use the global appearance similarity to transfer with similar results. It also wasn't. And then we even tried to transfer from the class that would give the best possible result to see what would be the upper bound of class-specific transfer. It's all in the paper.
Great, thanks. Any further questions? One in the back there.
Thanks for the talk. This is regarding the first part of the talk, and feels like going back to the pre-deep learning hype, like part-based models and stuff. Where do you think these ideas are going to converge? And we had lots of papers regarding part-based models, and they seem to work before we came to like learning and stuff, representing objects as parts and then trying to label them and things like that.
I'm not sure. There were no object parts in anywhere in my talk, also not in the first part. But you know, I'm a fan of object parts, and also even the first part is, you know, the source knowledge model is deep learned, so it is a deep learning model. But there are no object parts. I'm not sure if the question is if I would like to put them in there, and the answer is yes. I would like to put parts back in the soup, especially if they are semantic parts. Like wheels and handles and fingers, which are defined really by a human. I have a series of papers also on that. But what I have shown you today is just the atomic unit is just the whole object. We don't have a part decomposition.
Yeah, but it was more hierarchical, right? So if you learn to detect like wheels and things like that, you can also learn to detect.
Yes, we could. It's a great point, but that's not what I was doing. So the hierarchy there was a is-a hierarchy. Right. So a giraffe is an animal. We didn't have a part hierarchy there, but yes, it would be nice to have it all in one big backpropagable model.
Thanks.
One more.
Hi. So you were talking about knowledge transfer, and the information that you were using at the moment is objectness. So learning from the labeled classes about objectness and transferring the objectness into the new classes. Is there anything else that we can use? Any other attribute we can use other than objectness?
Oh, absolutely. In my talk itself, we also looked at lower levels forms of objectness, like vehicleness or catness, then it becomes class-to-class transfer. But if you think about something completely of a different nature, well, there is a lot. For instance, there are people, maybe Zainab will talk about that, I'm not sure, but there are people looking at attributes as a mechanism for knowledge transfer. That's really a different thing, right? In the talk I've shown today, the fundamental thing is I can steer MIL because that patch of the image looks like an object or looks like a cat or looks like a vehicle. It's a whole patch, right? And whereas in attributes, it's more like I know that I'm looking for a furry cat and I have furry something else. And the furriness transfer even across completely different objects. People in the literature are recognizing zebras based on striped T-shirts, which is very fun to see. So indeed, there is more. Then there are other things. There is part decomposition we discussed before that are also possible. Another thing you can do is spend more time analyzing the background than the object. Yeah. In other, I mean, this is a phenomenon also there in the work I've shown. A lot of the reason it works is because it figures out what the background isn't the object. But there is much more than what I've shown you.
Thank you.
Any others? Okay, I have one question then. So some of the recent work in the community has gone beyond detecting individual objects, and in fact you mentioned it there at the end as well, detecting relations between objects. Do you think any of these efficient annotation schemes can be generalized to efficiently annotating object relations?
Well, I sure hope so. For these data sets, we also have I didn't present it, but for what we did here, it's also primed by some efficient annotation scheme, which basically looks at groups after making boxes. But I don't have a very strong answer myself, right? I'm not sure if there is a paper, maybe I missed that. But definitely, as we go towards structural prediction, which here is just pairs of objects, it's baby, right? You really want high structures, like involving many object parts, 3D positions. Then as we go there, the more expensive it gets, the more I wish people will invest energy into making efficient annotation schemes there. I don't have a good answer today.
Okay, so lots more papers for us to work on in future. Right. Any final questions? Okay, thanks. Let's thank Peter again. Okay. So I'm very pleased to introduce our second tutorial by Ivan Laptev. Ivan is senior researcher at INRIA in Paris, and he's also an excellent member of our community, having also won an ERC award and Helmholtz Prize last year. And he's going to tell us also about reducing annotation effort, following on nicely from the first talk this morning, but now we're going to learn about reducing annotation effort in videos. So, thank you.
Okay, thank you very much. Can you hear me? So thanks for inviting me. Very pleased to be here. So I'm going to talk more about video in this talk. And especially I'm going to contrast it. So this first few slides to contrast it, what happens in static image recognition and in video, in particular action understanding. So we are in 2018, so we all know the huge progress the field has done in the past years, and these are just few examples which are partly random, partly striking to me. So there's object detection, of course. So this is an example of YOLO, very fast and very 900 classes, lots of progress in this. So you see that we can do, and pose estimation, this is another great success. So we know that Kinect has changed the pose estimation in 2011 when the new sensors came out, the depth sensor. So now we can get similar performance in RGB images anywhere on the street. So this is all great. And then, so these are known tasks which we can just do much better than before. And the new tasks, so just a few months back, so I've seen in a news article that Google had a discovery that they just put lots of images into the net and trained and discovered that from retina one can predict some diseases which doctors knew about, so like cardiovascular diseases, but doctors didn't know that this can be done from retina. So this is another way to diagnose people, which is great, right? And so here's a plot which shows a bit of history, what happened for object detection in particular, right? So most of you know all this too. So there's been much progress in the around 2007 through 2005 when the Hog detector came out, and so it developed to DPM and further methods, and then was stagnating around 2012 until the deep nets came out, and there's been huge progress since then. Right. So interestingly, if we now switch to video and action recognition, so the plots look a bit different. They're transposed, but you can see that it's almost that this works. Okay, it works a little bit. So we see here, so there's no timeline, but from descriptors you can recognize that around this time, so CNNs came out 2014, reached video and action recognition, and so you see that on both two data sets, which are main benchmarks at the moment for action classification. So we had a progress with so-called handcrafted features, but then when CNN came out, actually it now stagnated, so which is exactly the opposite of what happened in static images, which is interesting, and it's interesting to speculate what is happening and why we have this situation. What should we do about it? So the question is, what's wrong with action recognition? And so one natural answer hypothesis which comes to mind is the dataset size, of course, right? And so here's a plot of few recent datasets where you have on y-axis you have the size in terms of number of samples, and the circle of the blob is the length of the videos. Okay, in the dataset. So what you can see here, okay, so first you see that actually there have been quite large data sets like Sports 1M, which had about 1 million classes. But if one looks closer to this, so we see that actually these big data sets, two of them, Sports 1M and the YouTube, 8 million, so they have noisy labels, so it means they just, okay, YouTube, for example, it's a collection of YouTube videos with user-provided tags. Okay, nobody verified them. Same for Sports 1M. And so now if you look at data sets which are with manually verified labels, so we see that the scale of them is much lower, so about 1 order of magnitude lower. And this may indeed affect the performance, because we know that for static images object recognition we had to have a huge data set, and for video, usually the video networks are more complicated than static image networks, so we expect maybe the number of samples should be even larger, but it's hard to collect them. And so one observation, so kinetics, moments in time, but especially kinetics came out recently, and it did actually change the performance a lot. So this is a boost of i3D, and i3D is mostly not, is boosting performance not because of the architecture, which is interesting, good, but not, I guess, not as much novel compared to other methods. So what's really new is the new data set. So one hypothesis actually is that maybe if one takes the curve or the performance of just CNNs without any, because in these methods, in 2014, 15, 16, people usually combine the handcrafted features and the CNN. So maybe the CNN performance is actually is somewhere here, right? So maybe we are just growing. So we need more data set. But so there is a problem with this. Is that well, annotating kinetics? So it was done by Andrew Zisserman colleagues in DeepMind, so I don't know how much it costed, but it did cost really a lot, probably much more than ImageNet. So we can maybe just wait until Google, Facebook annotate data sets for us. So maybe this is the progress. Actually, I think it's not only about data sets and the size of data sets. So there is, for video understanding and for actions, there is much more. Well, there are other things which have to be addressed. And so therefore the second hypothesis why we are struggling with video and actions is annotation. So how do we actually annotate things? And so the common approach for doing this for objects, scenes in static images is to open a dictionary and to look up the nouns, which represent some visual concepts, and just search for them on the internet, filter. Okay, so we all know this. So if you take the same approach for actions, this has some troubles. So, for example, if you just take verbs, so they can mean lots of different things. In maybe open in English represents these actions, but maybe in some other languages they may be even called differently. And of course, like we may want to group all of this for some reason into one class, but obviously for functionally they are very different. And maybe when we are interested in actions, we are often interested not just in linguistic label for them, but sometimes yes, if you want to search text on videos on the internet, or open might be enough, or good grouping criteria here. But for if you want, say, learn a robot how to open a door, so like opening umbrella won't help very much. Right? So we need some. Well, and of course, if you look at this picture, then the argument is, yes, this is too coarse. Why don't we go to something more granular, like how we split? Okay, we say this is open door, open umbrella, and this is my favorite cat video, which you may have seen, which exemplifies this other end of the other extreme of action labeling. So this is a UK surveillance camera, and well, it was private surveillance camera. So people were missing cat, and they were for some reason they looked at this video, and so they found the cat. The police found the woman. They were happy, and so I'm showing this video. I don't know how many years, probably I think 8 years. You must have seen this. So, but the situation didn't change. So if you want to well, if this is your cat, even if you hate surveillance cameras, you want computer to realize that something went wrong in here and to save your cat. So how to do it? The answer didn't change over the last 10 years. We need to get lots of PhD students or mechanical Turkers, find videos on the internet of this type, like person throws cat into trash. Okay, so this is not going to work, right? So we have to, actions are compositional, we have to decompose them. So it's, okay, so it's not just labeling. So we have, if you want to, like we started this discussion, so if you want to come up with a set of labels for actions, so we have a problem with just opening a dictionary and taking a list of verbs. And we also, because it's too generic, it also becomes very specific if you really go to specific events. So what to do about this? This is an open question. And so another related question is ambiguity. So the same action in different situations can be called differently. So if I ask you what are these people are doing, you would say what? Running, yes. And this is a full picture, so now you may call them differently. So again, so how to name actions is complicated. And again, so maybe you say I don't care, so I just take whatever names. But then, of course, if the classes overlap, or if you say train your CNN with a softmax clause, which penalizes just wants to train for one action, penalizes all the others, so then it will penalize. Well, if you train some multi-class classifier, which assumes that one sample can have different labels, you still have the problem because your action will be labeled only with one label. So labeling of actions is unclear, and maybe this is another reason, apart from the data sets, this might be another strong reason why we are struggling with video understanding. So in this talk, I would like to just show some of our recent efforts which go these directions to address the problems which I just mentioned. So I tried to go through 5 papers quickly, and if you have any questions on the way, by the way, so please feel free to stop me. Okay, so the first one is about YouTube. So this was in the context of the YouTube challenge, which was last year. I think it happens again this year. So YouTube, they collected, I mentioned it in the beginning, so there was this big gray plot in the data set diagram. So it's around 8 million videos, and they have no verified labels or tags. So they have tags provided by the user. So these tags are inherently incomplete and noisy. Still, it's interesting to predict what are the tags for particular video. So, okay, so found actually 7 million videos, about 5,000 unique tags, 3.4 labels, like tags per video. So lots of data. Actually, the particular thing about this challenge was that there was so much data that it would not be possible to download it, and unless you are Google, Facebook, you would not be able to compute all the features. Anyway, so features were pre-computed, which makes it a bit less interesting. Still, given the scale, it's an interesting. And given the scale and the fact that this is a real task, so it's not some benchmark which came up by researchers. So this is a real data. You want to predict the human tags as good as possible. It's interesting. Okay, so that's the data set. And okay, so why it's interesting in this talk? It's the context of noisy labels. So we want to learn from these noisy labels as good as possible. So here are some results. So we were lucky to be first in this challenge. So that's why looking into this method makes it a bit interesting. So usually challenges are kitchen sinks where you put together all possible things, and of course our students tried this as well, but so we tried something more. So as I said, so the features were provided. Okay, so there were actually video features and audio features, and so the main task of this, all the teams, you had a possibility of accessing the real videos and train from them, but so all the 650 teams participating, they focused on basically aggregating the visual and different forms of aggregation for visual and sound features. Okay, so that's what we did as well. So there are two interesting findings here, which I'm going to briefly describe. So first is LSTMs. How many of you know what LSTM is? Okay, good. So you don't need to explain this at all. Okay, so LSTM is a recurrent network which recursively combines the information from different time stamps for sound, for text. It's a sequential classifier. Okay, so we tried LSTM. So, but alternative to, you can see LSTM as an aggregator. So we provided set of measurements in a sequence, okay, and you hope that LSTM or RNN, they learn something about sequence and give you some better result than just, say, average pooling. Okay, but alternatives which are more common in vision and been used a lot before CNNs for, say, image classifications are bag of words, blood, Fisher vector. So if you are not too young, maybe you heard of them as well. So, and now, of course, so these were non-trainable. So all of these have parameters. They were not trainable. Currently, now we can construct CNN layers which sort of mimic, not exactly replicate, but mimic this type of aggregation techniques. Okay, if you never heard of bag of words, I assume you did, but so it's in contrast to RNNs or recurrent like LSTMs, so they are set aggregators, so they are not looking at the sequence of measurements. They're just aggregating it as a set, your measurement, assuming that your measurements are unordered sets. Okay, so that was one difference, and I guess I will tell you when we come to results, so I tell you some interesting findings here. And the second, more specific to the problem which was given here for noisy YouTube tasks. was dubbed context gating. And so imagine, so you have this video. And so this video, if you are a user, you may tag this video with snow, skiing, something else. And so what we observed that if you have a great CNN network, CNN classifier, which now trained for objects, and you apply it to this image, so it will produce something like this. So it will tell there is well, ski is actually quite hard because you just have the tips of the ski. But definitely you see snow and you see lots of trees. Thing is that if you are a user and you are tagging this video, it's quite unlikely. Well, you will label what you are interested in, what's important for this video. And arguably the trees are, well, if you are skiing, it's very common to have trees. So people won't label this video exhaustively, so people will just label tags which are interesting. And, but if you apply the network, so it will exhaustively just list all the labels. That's one thing, and another thing that because you will have, in the annotation, you will have missing 3 labels, so it even get more confused. So, the one treatment of this problem is the following: is that instead of having just so the standard network, so it will have convolution layers, maybe some average pooling or fully connected layers, but it will be always first order operation. So the trick here is to introduce a second order operation. It's known as under different names, so it can be called gating. It also appeared after this work, or in parallel, it appeared as in squeeze and excitation network as a part of the upgrade or some addition to the convolutional layers. So the idea here is that we are not just, so the fully connected layer would be just this, right? So you learn, so there is a matrix of weights W, the data X, so data means some output of the previous layer. For example, if we are at the very end of the network, just before classification, so this could be the action scores or the label scores. So, and but instead of having this first order operation, so we are having this first operation, but then we have also element-wise multiplication with the data itself, with the X, which gives second order operation. And in this way, we can train network, or the network trains to actually suppress things which are not interesting. In this case, okay, this is a schematic. I'm not claiming these are real numbers, but what happens, we've seen it in many examples where the labels which are correct objectively, but just not typically annotated in the video, they would be suppressed. Okay, and that's why the name here, context gating, because the network learns something about the context of the video, and then learns weights which would either amplify some concepts or decrease the likelihood of concept depending on the context of the scene. And so you can put this layer, as I said, just before the classification layer. You can put it lower in the network. We didn't try it for convolutional layers, but so squeeze and excitation and some other papers, they now put it into convolutions, and this usually helps. So it's an interesting operation. So for the challenge, okay, so now for results. So this is some ablation study. So first, maybe I mentioned the recurrent networks and the net flood. So as you see here, the performance, so before gating, the performance of greens and the recurrent networks perform less good, which is interesting. We also tried, so recurrent networks, they are supposed to capture some order of the data. And so in our experiments, even if you take your video, okay, you train RNN or STEM, If you reshuffle the frames in a random order, it performs the same. If you reshuffle frames in a different order and just use it as a data augmentation, the results improve. So suggest that if you use LSTMs, sometimes LSTM probably don't capture anything about the sequence. So it's a good check if you are using recurrent networks. So it's a good check to verify to actually, if you are writing in the paper, I'm learning the sequence of something. It's maybe actually RNN is not doing it. So and then the second improvement is from gating, right? So it really boosted all. Well, actually, it was not. It's not presented for. Okay. It's not for presented here for recurrent network because they already have gating inside. So it would not help. Well, actually, it did not help to put gating on top of it, but it does really help to put gating on top of NetFlood and Fisher vector. So some results for. Depending on the number of training samples, so because this data set is huge, so we can really study by decreasing orders of magnitude, going from hundreds of thousands, going to, say, 10,000. So what happens, so we see that the gating does improve in all the, for all sizes of training sets. So also what here this plot is showing is the lower curve, the blue cyan curve is showing the average pooling. So average pooling is lower, so recurrent networks do help, but the especially gated net flood average aggregation is good. Okay, so here are the top 10 teams. So, okay, so now switching the topic a bit, so still about video as through all the talk. So here is a more recent work about where the goal was to train it text like video retrieval by text. So it's not about labels anymore. So we want to train a network where you can just type text and retrieve videos from internet or from your database. Even if you don't have labels, so the problem is of annotation is or supervision is still there. So there are fewer data sets where you have videos annotated with text. Okay, there are maybe okay, you can take YouTube and sometimes people describe or narrate what is happening there, but this is not verified. So like data sets we have clean descriptions of the video are quite rare. So to fight this, so this work tries to combine heterogeneous data sources, and so this particular example here on the slide is that even if we have, okay, so say we have some data set which describes video by text, but it's small, doesn't say, you cannot learn all the objects from it, for example. So you could take a pre-trained network, of course, but so we have a method which tries to simultaneously learn the network from different types of data sets. For example, we could combine, okay, so this slide actually shows what we are combining. So we can train from videos, and there we can extract motion or appearance. We can train from still image data sets, from video, or we can train from pure audio data sets, and even images or videos. We can also extract face information and add it as another queue in the model. Okay, so the idea is to have the model which combines different sources of data, like audio, motion, appearance, and more specific cues like faces, maybe a human pose, and so on. So that's on the vision side. So now we want to learn the video retrieval. So it means text in, or more generally want to learn association between text and the video. And the model here, which is a bit different to other similar works, so it has an embedding. So each of these data sources, it will generate an embedding, so some feature vector. And on the left side, so you'll have also embedding, and which will be different for each of the sources on the right. Okay, so for example, for appearance, we'll have one embedding. For motion, we'll have another embedding. For text, and so on. Okay, so and then the score. So now, if you want to score if the video and text do correspond, so we just do, given the embeddings, we can have a combined score, which which makes a dot product between embedding for text, embedding for corresponding source in the video, and sum them up and get the score. So what's slightly novel about this method is that apart just from combining the different sources, it also has this learnable weight. And this weight, which is typically would be fixed for, say, I trust more motion in general. I trust, say, I don't know, 50% motion, 10% faces, maybe 20% appearance, and then the rest something else. So here the weights, depends on the data. And one can make them, the weights depend on both video and text. So in this case, so weights depend only on the text. So given a sentence, so the sentence does, after the network is trained, so the sentence does generate embeddings for each of the Q, and it also generates a mixture weights specific for this particular sentence. Okay, and then, so I guess maybe I'll go to results, and then it will become more clear why this is interesting. So data set, there are not many, so there are two data sets for two main data sets for where videos are annotated with text, where we can apply video retrieval. So here are some results. So if we apply the network and use the gated embedding, so just what we have shown you in the previous part of the talk, so we get some boost. And now if you try to start combining different modalities, so if we add face here, so we get improvement. So if we get, if we add the, so we train the videos and text, and now we also add the objects. We add the COCO data set, which knows a lot about objects. So it also boosts compared to baseline. And, so if you combine them, so we get improvement. So if you have any questions, so please can take them now later. So the results are good for overall the state of the art. So the demo, actually the retrieval demo is online, so you can try it yourself. So it's not searching YouTube, it's searching the MPI data set, which is quite large, which is about, I think, 100,000 or more video clips from movies. So you can type things like a car crash, and so it will find it. So you can type things, people dancing, so it will find people dancing. And then you can try more specific things, for example, focused on faces or focused on motion. For example, if you type people dancing in a nightclub, so maybe, didn't check, I don't know, cannot swear, but maybe this data set didn't have actually a training data, maybe didn't have the nightclub, but if COCO had the notion of nightclub, then the network would be trained to combine this knowledge about scenes, objects, and the fact that how people dance, which comes from video, and so that's what the network is finding. So it's interesting to look a bit back on the weights which the network has learned. So So if you remember this diagram, so we had embedding for different modalities, both in text and in vision. And we also had a weight, which is a modulator function, which would prioritize some modalities depending on the concrete example. So here are examples where the weight for, in this case, for facial features was particularly high. And so this weight, again, so this is generated just from the text. So, what this slide shows that indeed, so if you look at examples which have this highest weight for faces, so we see that the text actually does describe often something about people, okay, a rounded faced woman, or gender at least. So she looks, he enters, she's standing. So it's likely that the network, to retrieve this video, the network is amplifying the knowledge about faces. So because the text mentions she looks, so the network will be looking for videos where there are females, for example. Same thing for other modalities. So here's examples with the highest weights for motion modalities. So, not surprisingly, we see many actions. For appearance modality, we see examples where there are lots of text, typically describing objects and scenes, like cars, kitchen, fridge, and so on. So here we can imagine that the network is using more knowledge, which was trained not actually on video data set, but from say, COCO data set. And for sound, similar examples were given for sound. Okay. Any questions? Okay, so then I'll talk one more work which we've done over time quite a bit, is looking at, again, text and videos, and in the context of movie scripts. So movie scripts are great because they often describe the content of the video. Not exhaustively. There is no correspondence between text and say, the text is saying that, say, Sam is in the scene. We don't know who is Sam here, and so on. Okay, but for many movies, there is lots of knowledge embedded in the scripts and in videos. So the question is how to dig this knowledge out. So we had some work quite some time ago, which was looking at particular slice of this problem, interpreting the faces and actions together. So one can do weakly supervised. So given the script, so there's been lots of work of associating faces with particular people without additional supervision. So one could do the same for actions. So this focus of this work was to do it jointly. And the reason why this could be useful to do it jointly is this situation where we have, say, a sentence which is Rick walks. So if we reason about the people and actions jointly, so we may just narrow down the set of hypotheses to remove the other hypotheses which are not the same. So here the same person should be Rick and should be walking. So what's the problem here? It's a weakly supervised learning where we don't know the correspondence between text and the image or the video. And the framework which we use quite a lot, have used quite a lot in the past, for this type of problem is discriminative clustering. So this is a loss function, which is a quite standard loss function with the difference that it has two things. So one is the X is the data, W is the classifier, and Z are labels. And if Z is given, then this is a standard supervised problem. We don't have Z, so it's unsupervised problem, which would have degenerate solution in general. But, okay, and say this is, okay, for faces, you would have face descriptors here, you have a classifier, linear classifier W, you have labels of faces. So if you are just giving if you are trying to learn Z and W together without any constraints, this is going to fail because there are lots of trivial solutions for this. But what makes the problem regularized is additional information which you can get from scripts. That's the goal of this work, is to try to get as much information which is available in the text but not directly connected to the video, and construct the correspondence between video and this text. So here is one way to construct the correspondence. So this is the form of Z, which is, say you found all the people by your favorite person tracker. So each row of this Z is a person track, okay, and so each column of the matrix corresponds to one of the common characters in the movie. Okay, so say if you have in Casablanca movie, you know, from the cast there are 20 main characters, so you just construct 21 column in this matrix, so one for anybody else than the main characters. And now, because you don't know very much from the script, but you know that maybe in this 30 seconds of the video, Rick was there because it was mentioned by someone or so. And then you can put a constraint on this matrix. So these are all the tracks appearing in your temporal window. And this is a column for Rick. And if you believe the Rick was there, so you can just put constraint. Okay, so this is a linear constraint, quadratic cost. So the good thing, nice thing about this formulation is that it can be solved in a closed form. So you don't need, actually, okay, this can be solved in a closed form. And if you put constraints, so it's not closed form, it's a convex thing, so you can, if you are not training features at the same time, so you can converge to actually optimal solution. Same thing for action. Just instead of person labels, you have action labels, and then you can combine them into a single formulation. So that's nice framework for weakly supervised learning. You can extend it. So we have used it with CNN features, but without actually fine-tuning them. So now you can also, there are papers coming out where you can use this loss for fine-tuning the network. So so the work we did recently is to scale up this to lots of data, and scaling this to lots of data has issues, because if you put so faces you can train separately for each movie, but if you want to train actions from lots and lots of movies, then your Z matrix, or so it was called here the T matrix, so it becomes huge because you have to put in it the tracks of all the movies. This becomes, and then solving these equations also becomes tricky if you have very big matrix. So this paper was proposing to do it blockwise in a batch fashion, and so it was the contributional paper. And so what's practically interesting is indeed that you hope for, and that's what happens. So if you train from 1 or 2 movies, which was possible before in our case, so the performance was around 12, and so training it from more and more movies, just so it brings performance much higher. So here are some results first for faces. So here's modern face descriptors, which work very well. So they enable to cluster people very well. So what happens here? So you are given the American Beauty movie and the script, and then all association between the faces and the names, it's done completely automatically. So it's very clean. So there are about 20 characters in this movie. So all green means that it correctly classifies them as unknown people, and it puts the names on the main characters of the movie. Okay, and exactly the same method now combined for action and person labeling. So here are the results where we give the algorithm videos with scripts, and it distills the actions and the names of which are present there and attach them to people. Okay, so I have 5-10 more minutes, so I want to switch to, actually there's not much switching, so it's just going more into a bit different domain. So it's, we are learning from instructional videos. So we worked quite a bit with general action recognition, and this is fun, but so this labeling problem which I mentioned at the beginning, how to label actions, it's often leads to the conclusion that to define the labels, you actually need to have some task in mind. So if you don't have a task in mind, it's defining actions generally is there is this problem of ambiguity, of granularity as well. So the instructional videos domain, it's interesting by itself, and it also gives this possibility of looking into actions in the context of specific goals, which makes them more defined. So what are instructional videos? I assume all of you know. There are lots of videos on the internet, like this one. So people are learning other people to do things. For example, changing car tire. And they are not just showing it, they're also narrating it. So they are carefully explaining what they are doing and why they are doing, and maybe some other irrelevant things. So the good thing is that there are lots of videos. So I say if you search for changing car tire, you'll find not just one or two, you'll find hundreds of them. And so many of them are quite consistent. So even they are not done to be consistent, they are doing the same task. And okay, maybe there are 2-3 different ways to do the same task, but in general, there are many repetitions in them. And of course, not just one task, so you can search for lots of different tasks. So, so the fact that these videos are done by people to learn people. So, question: can we learn computers to do this, to understand the tasks, and maybe later, so how we can. So once computers have understood what the tasks are about, we can think of different applications. But first, and maybe one of the motivations for us to look into this is that here we don't actually need to provide the labels. So we should, for actions, we want to get the important actions directly from the video. And what's important can be debated. So in our case, we just say that actions which are repeated, so if somebody scratches the head in some point, so that's probably won't be repeated, so it's uninteresting. If people consistently first unscrew bolts and then take the wheel, that's probably actions which we should be caring about for the task of changing a car tire. What's applications? Potentially, so if we know how to perform a task, we could maybe construct automatic assistant, which will, for people who are doing some work at home, or maybe for industry people who have lots of complicated tasks which are complex and different, so there are not enough experts to know all of them. So the automatic assistance for people how to perform tasks is interesting, and in the future for robots, so can we learn robots how to achieve tasks just by looking at the internet? So that would be great. Okay, so you want to, another way to say it, you want to replace this type of instructions by by something which is much better and understandable. Luckily, so the problem here actually is not very different to what I described you before. So we are given we again given text and we are given video, and we want to find the correspondence between text and the video. So we want to do automatic clustering between in the text and in the video. So difference to the movie work, which I've shown, is that in movies we have given the labels manually. So here we don't provide any labels. So we really want unsupervised discovery of actions in text and the video, and of course they should correspond. Okay, so I won't go through all details there in the paper, but so clustering text and clustering video. Clustering text is still much easier because it's already semantic. So it would be nice to cluster text and video jointly. So because the problems are so much different in the complexity, so usually it helps to first cluster text and then with the help of text clusters find the corresponding action clusters. Okay, so if again this running example of changing car tires, if you take text, so we may find some examples of actions, and as you see, so these are examples of the same actions, and they are already very different in text. So text clustering is non-trivial, and of course, like clustering in appearance is also non-trivial. So the what the method is doing is trying to resolve these ambiguities. So method is similar. So what is changing again is the constraints. So as we don't have labels, so we have some other constraints in this work, and they again help for the clustering. So data set currently quite small. We are in the process of making it much larger. So 2 years back we had 5 types of tasks and maybe about 150 videos, about 100 videos for each task. Oh no, 30 here. Okay, maybe it's grows since then. And so currently we are working on making this type of task like maybe 10, 100 times larger. So here are some results. What the method is fine. So these are, so it's a clustering, so you can set determining the number of clusters or actions is well, it's a different problem which we're not addressing. So we're just saying that I want for this task to find me, say, 5 most important actions, and so here are the ones which it finds. And as you've seen on the previous, in the video, so it was able to localize them also in the video. So same thing for making coffee. Okay, so last part, just going very briefly, is related to what I just described. It's just enforcing it and picking up another aspect of videos, and especially instructional videos, is that actions, well, they can be kinematic, just waving hands. They could be interactions between people. Often the purpose of actions is achieving some manipulating objects. And so basically if you are pouring, if you are making coffee and you want to drink coffee, so at some point you should have an empty cup and then pour coffee in it. So that's otherwise you cannot drink it. So there is in many cases, a very strong relation between the states of objects and actions. So actions are there to modify the states of objects. This is the goal. So we want to capture this again automatically without any labels. So this is quite difficult task if you don't want to assume anything. So here we assume that at least we are giving short clips where we know that some state change of a particular object is happening. So for example, so we are giving the clips where we are pouring the coffee into a cup. Okay, and so inside the method we want to discover, well, first when in this clip action is happening, and then also discover what is an empty cup and what is a full cup. So we assume here we again make a bit of simplifying assumptions. We assume that the cup detector is given to us. But what we don't know is when the action happens and what is actually empty cup and what is a full cup. So these three things we want to discover. And we hope that, because we believe that the state of objects and actions, they are very related. So hopefully the discovery process should be helped if we do these tasks jointly. So if we discover the state of cups and if we try to automatically find when the action happens. Okay, so some example with oysters. So we have say oyster classifier and the output, which is noisy, but the output of the classifier of detector, sorry, of the method would be well, classification detection of oysters into different states and detection of timestamp for the action. Okay, so I'm skipping details of the method. They are somewhat similar to what I described before, just adding to the actions, we are adding the weakly supervised clustering of object states, and so that's what comes out. So we are able in our videos to find out, discover, so the empty cups, the action of cup being filled, and then the full cup. And again, so the constraint here is really to separate. We know that the state 1 and state 2, they should be separated by the action. So this is a constraint which we just provide manually, which is logical. And so in terms of results, you can see that, yes, indeed, it helps. So if we just do only states or only so there are two types of relation. We can evaluate the state classification or action localization, and doing these two tasks jointly helps for both of them. Okay, so that's about it. So I finish with so what we are currently looking, we want to scale up. So there are lots of tasks on WikiHow and on YouTube. So there is a potential to scale this up. And so there are interesting questions which come up, how to learn this from this very large scale and noisy data. So also interestingly, so this we are in the process of creating data set, and so this data set, it will be our first real data set. Second, it won't be trimmed. So usually most of the current data sets, they are taking the particular actions. So it's a classification set. So here there will be a sequence of actions. It won't be a random sequence of actions. It will be a sequence of actions which is will be targeting particular tasks. Okay, so that's the high levels. One can, of course, look more into details, how people manipulate objects. That's more related to the very last part which I described. So also looking at hands and objects, how to reconstruct this, how to reason about actions using the more fine-grained models of object manipulation. And of course, so once this is done, so one can imagine that this could be very useful for robots if we know how people manipulate objects. So these models could be transferred to robots. I'm not saying this is easy, but let's believe this would be an interesting information which could help robot to learn not just pure reinforcement learning by trial and error, but having more supervision from real data to towards specific tasks. Okay, that's it.
Okay, thanks for that great talk. Do we have any questions? Okay, I'll start with the questions from Twitter. So, what do you think is the reason for the poor performance of recurrent models in action recognition? Does this mean that there is not really any temporal information to be exploited here?
Yeah, so maybe, maybe the answer is that the current data sets, so most of the data sets, they are about holistic actions where actions are not composed of, it's not a sequence of different steps which can change. So it's more like a car. So when we are like doing a car detection or classification, so it's, we can assume it's just a holistic object. We can ignore the fact that we can model it by parts, but current state of the art tells us that it's not even necessary. So I believe the sequential models, they will be more meaningful when we will have a sequence of things, which actually may have like a tree of different endings. And so I don't think that recurrent models are useless. I just think that in the current tasks which we are addressing may be too simple for them.
Okay, thanks. So one more question from Twitter. Do you think current methods for action recognition focus too much on the background instead of the actions themselves?
There is certainly an aspect of focusing on the background. We know that the motion features, they are very powerful, and often background is static or moving homogeneously. So I don't think it's all about background. But yeah, definitely there is an aspect of scenes. Of course, if you exclude background, the performance drops. You know this.
Any others? Okay, I have one question. So one of the reasons for apparent label noise when working with these real-world image tags can be polysemy. Maybe different users prefer different meanings of the word. One user likes rock music and another user likes rock climbing, for example. Then the word rock can mean something different. Do you think there is some role for learning user-specific models for tagging, and if so, how might we do that?
Okay, sure. So you would need to have some training data, user-specific training data, which I imagine could be done. You can maybe like categorize users, I don't know, into 100 categories, and then provide results, user category specific results. I think this could be easy to do, and one way to do it is also the part with the learnable weights, which I've shown. So the thought work which I've shown, I guess, so one could just imagine to directly use this and learn weights, which would know about some, which will, in addition to the text provided by the user, so there will be also label of the user category provided into it, so the way it could be learned to adapt to the user. I think that's, I imagine this could be easily done, but we don't have data to try it out.
Okay, great, thanks. Any final questions? Yeah, got one.
I just want to ask one question which is related to the previous Twitter question and your answer to that. So currently for video classification, we have like frame-wise level also for representing each frame for each time step or set of frames for set of time steps. How do you propose that we represent this as a holistic way? For example, 3 seconds video. Mm-hmm. How do you expect that it can be represented in a more holistic way instead of frame-wise level? Mm-hmm. Thank you.
So I think doing it, interpreting frame by frame and then aggregating at some very high level, I think this is, I don't think this is any good way, because you are losing all the low-level motion information, which is interesting. So I think having the convolution starting from the very, very beginning, from the lower layers, this is clearly useful. But then the question is, yeah, so you can maybe do it for 1, 2, 3, 5 seconds, but then of course you cannot, you won't have enough memory to like keep all the like 1 hour movie in. Sorry, what the question? Can you? Yeah, how to represent this? So, okay, the current, I think, the consensus, which seems plausible to me, is to do sliding window convolution and to get some feature out of it. And so one could imagine, actually, so yeah, so it doesn't, maybe so recurrent, and people tried it, so they not with a huge success. But to me, it would be natural to see at some point to having the convolutions and recurrent modulus like on all the layers of the network, and then so the temporal aggregation would be and then you would have a sliding window and with a recurrent modulus, which would keep some memory of what happened in the last 15 minutes of the video. So I think that seems logical. I haven't seen people. I've seen people trying it, not with a big success, but maybe this will change in the future.
Okay, great. Thanks a lot. Let's thank Ivan again. And now it's time for the coffee break, so enjoy your coffee and we'll see you back here in 45 minutes.